start with the first speaker, Krishnendu Sengupta from IACS is here. And over to you, Professor Krishnendu.
Okay, I guess I'm audible. So, me here, and I'm going to talk in my set of 4 lectures about how what is meant by quantum chaos, actually how chaos essentially shows up in quantum systems. And so the first lectures would be on the initial attempts to understand this chaos through random matrix theory. Then I'm going to go to something called, in the second lecture, to something called eigenstate thermalization hypothesis, which is our current way of understanding how these things work in quantum many-body systems. And then in the last 2 lectures, we are going to show 2 ways of violating this conjecture where this doesn't work. And this is rather, not the norm, but it's exception to the general principle. So I'm going to talk about those. Let me start by, from really simple things. And so when we talk about chaos, the first thing that comes to mind in a classical system is trajectories diverting apart, right? So in general, if you have a classical system where there are trajectories of particles, then chaos is defined by exponential sensitivity of these trajectories to its initial condition. That is, if at t equal to 0, I'm going to have a distance d0 between 2 such trajectories, then as they go on, at a later time, this difference is going to be, and this lambda is called the Lyapunov exponent, and that's just the leading behavior. Okay. So this means that the system here follows deterministic equation. Okay, so there is nothing unpredictable about that, but the unpredictability in practical terms comes from the fact that these trajectories, their motion is really, really sensitive to the initial condition. So, if you just change this initial condition a little bit at a much later time, you are going to get a completely different result. Okay, so the prediction of long-time behavior requires very precise knowledge of the initial condition, and any amount of error in there just gets exponentially multiplied. And that's where the setting of chaos comes in. Okay. Of course, these are some fancy names, butterfly effect and all that, but I'm not going to get into that because my main topic is the quantum version of it. Okay. So in quantum mechanics, what is the analog of these trajectories? Okay. So first, let's try things one by one. So suppose I try this thing with wave functions. Okay. So let's say I have a wave function psi1 of t. Okay. And I would like to see that 2 such wave functions, psi1 and psi2 of t, whether they are going to show similar properties. Well, I can, since it's a Hamiltonian evolution, I can always write this as some this wave function can be expanded in the energy eigenbasis. That's straightforward. And same way, I can do this with the second one. So I can just write 1 or 2 and the same thing. Okay. But now, if I take the overlap of psi2, psi1, you are going to see that these are independent of time. That follows from the orthogonality of this energy eigenbasis. And this is just given by Cn star summation over n, Cn star 2 times Cn1. Okay. That's just a number. So clearly, wave functions cannot play a role of trajectories in here. That's not a big surprise. Wave functions are a very different beasts. But the point is that since this happens, one needs to think about ways of implementing chaos in a quantum system. It's not straightforward. Okay? And initial attempts to this were done in 2 different ways, at least to the best of my knowledge. There may be other parts in the literature which I'm not aware of, but one thing was people trying WKB. So they wanted to define trajectories in phase space. Okay? through this WKB approximation, and for semi-classical systems, this is supposed to work. The problem, and then talk about properties of those trajectories. The problem with this comes that in many of these quantum mechanical systems, these trajectories are not closed, particularly in ergodic systems, and this doesn't work very well for those. Another thing, which was a work of Gutzwiller, what he did is that he wrote down the Green's function of a system in the energy basis, omega epsilon, as, let me just write it in Matsuba imaginary frequency. So he defined a quantity like this, okay, I omega m, sorry, this chalk is, okay. So defined it like this, summed over all energy. It's just the Green's function, but you sum it over all the energy space. And that is by superposing these different energy eigenstate, he was trying to create a semi-classical description. And if you massage this a little bit, you can show that this thing can be written as some sum over classical paths in real space, x prime, omega m times some exponential minus s over h, where s also depends on these variables x prime and x prime are real space coordinates. So it's just taking it from this, from the energy space to the real space. This is easy to do for integrable systems or simple systems, but very complicated in case of ergodic systems. And the analogy was then, using this action out here, you can talk about classical trajectories, and in terms of those trajectories, can you quantify chaos? And this method didn't go very far because of the calculational complexity, because converting this to that is going from the energy eigenstate to the real space, is a tremendously complicated stuff. Okay. So this classical trajectory method, or rather, taking a quantum mechanical system and trying to find out trajectories from it, didn't really fly. There were initial attempts, lot of attempts in 50s and 60s in different ways, but that didn't work out very well. What did work out was a remarkable observation by Wigner, who was studying this nuclei, very complex nuclei, and he was looking into the energy spectrum of those nuclei and the corresponding eigenfunctions. So basically, his thing was, is there a way to push this? So I should, okay. Yeah. Okay. So what happens is, he was studying this energy spectra of a complex nuclei, and then he observed that this exact energy eigenspectrum and eigenstates of a complicated quantum systems are just too complicated. It's much easier. I mean, it makes much more sense to focus on the statistical properties of them rather than trying to understand their individual properties. That was the first leap, because statistical properties of a closed quantum systems were not a fashion in those days. This was really the first half of the earlier century. So what he conjectured was that if you take a small energy window, epsilon, such that the density of state of these complicated energies are constant within that period, rho epsilon equal to constant. And in the next class, when I'm going to in the next lecture, when I'm going to talk about random, this eigenstate thermalization hypothesis, I'm going to talk a lot more about this window, what this actually is. But let's just say that there is this small window epsilon for which this rho epsilon is a constant. Then his conjecture was that if I look into just this window and try to write down the Hamiltonian in a generic basis as a matrix, these matrix element Hij are uncorrelated random numbers. Okay. Rho epsilon is the density of state. And they obey a Gaussian distribution. Yeah.
What does it mean to write the Hamiltonian only for a small energy window?
Well, you can think of this. So you can write this Hamiltonian within any energy window, but the prediction of taking this Hij to be uncorrelated random number and deriving properties of this, that's going to work if you are looking only within the small energy scale. Okay. So the point is that, so these looks like uncorrelated random numbers, and the point about that is that since this is a many body system and there are lots of these, and it's only natural from central limit theorem that they're going to follow a Gaussian distribution. Uncorrelated random numbers, lots of them. So essentially, he took that this Hij follows a Gaussian. Now, with this, he was able to derive certain properties, and I'm going to sort of illustrate this in context of a two-state system. That's the simplest thing to do, where one can do some analytical calculation, because rest of it, if you take larger systems, it's mostly numerics. So let's try to do this and see where it goes. Okay. So, two level, and I'm going to take this Hamiltonian as some diagonal elements epsilon 1 and epsilon 2, and then there would be some, ignore this factor of root 2 for the moment, that's just for, this is what happens when you put in factors. Okay. Ignore this factor of 1 over square root 2 for the moment, this is just for calculation and simplicity. We'll see that the calculation becomes a bit easier if you put that. Now usually, there are two classes, one in which these elements are all real, and this is where I have written this Hamiltonian, and the other one where here I should write a V star over square root of 2, okay? So that these are complex. So I'm going to do this calculation, the first part of it, just for the real Hamiltonian, okay? Because that's a bit simpler compared to the complex part. And all of this, epsilon 1, epsilon 2, V are random numbers with probability distribution which are Gaussian. Okay. Sigma is some, sigma is some basically variance of that Gaussian distribution, and we are going to take the same variance for all of them, just for simplicity. Okay. So the first thing one does from here is to, and what we are going to do just as an exercise is to find out how the energy gaps behave. What is the probability distribution of the energy gap if these are random numbers with this distribution. Okay, so that's the thing that we are going to do. So let us just find out the energy of this Hamiltonian first, treating these to be random numbers. So that is simple. You can diagonalize this 2 by 2 matrix, and you are going to find that this there are two of this, E1 and E2, which are given by, okay, so the sum and then plus or minus square root of the difference plus 2v square. Okay, and there should have been a 4v square here, that's the standard formula, but the point is that I have written a v by square root of 2, that's why this 2v square comes in. Here's the standard this thing. Okay, till now any questions, anything which is, I'm sorry? 1 by? Px. That is Px. Root over 2 pi, sorry. Okay. You have to excuse my handwriting. I mean, it's terrible. Okay.
Yes, suppose.
Yeah. Yeah, please.
Can you again quickly say what's the motivation that we are studying this random numbers and random matrices?
Oh, this was this Wigner's original observation in context of complex nuclei. Okay, that there are simply way too many eigenstates and eigenvalues, and this is something that you also see nowadays in a standard many-body system, because the Hilbert space is exponentially large in system size, even if you have a finite system, and so there are too many of these, and these are complicated objects. And his thing was that if I didn't want to know all the information about all of them, but if I just want to know about their statistical property, what can I get out of it? And in doing that, his conjecture was that this matrix element in a generic basis is like a random number. Okay. And then from that, we are going to derive whatever we can about this, So we are going to see how the level spacing would behave if you denote them to be a random number. This is relevant in chaos because we are going to see how this chaotic properties and etc. comes in here, but that will take this and the next lecture. So yeah.
So, what was the idea or motivation behind taking the matrix elements as random numbers?
Because the point is that if you have a very complicated Hamiltonian, so if you see. Experimentally, you just look at the spectra, right? So if you want to mimic that spectra by putting in a Hamiltonian, and if the spectra is complicated enough, it's very difficult. So the point is that if you now say that you want to look into only the statistical property of that spectra, the reasonable thing to start from is start from a a random Hamiltonian. And here, so now how do you start with a random Hamiltonian? So Wigner's guess and his intuition was that if you write that Hamiltonian as a matrix in an arbitrary basis, a generic basis, then this would behave like random numbers. That's the intuition, that's not something that you can derive, in some sense. This proves to be true in some sense, but yeah.
But you have to maintain some symmetry.
Yeah, of course. So, for example, for this kind of thing, it's orthogonal. There will be orthogonal. This will be symmetric under orthogonal transformation. If you have a unitary, it would be symmetric under unitary. So, all the symmetries are going to be taken care of. But after taking care of them in a generic basis, this will be the case.
Why do we take the matrix elements to be random numbers instead of taking just the eigenvalues to be random?
But eigenvalues are not necessarily, so I'm going to come to that actually. Eigenvalues are not necessarily random in a setting like this. We are going to see in a moment why. Okay. We'll see what happens if you take eigenvalues to be uncorrelated random number. That gives a completely different class. Let me just derive this and then we'll see. Okay. Okay. So now from here, the energy gap is E1 minus E2, which is of course just this part. Sorry. Which is just square root of epsilon 1 minus epsilon 2 whole square plus 2b square times 2. Okay, just the difference. So what we need to do is to sort of, sorry?
The 2 will not.
Yeah, sorry, there is a half, so the 2 is not there. So the point is that what we need to find out is now this is my energy spacing between for these two levels, and we want to find the distribution of this energy spacing. So let's call it, so this distribution, some p of omega is given by d epsilon 1, d epsilon 2, dv delta of omega minus this quantity, square root of epsilon 1 minus epsilon 2 whole square plus 2v square, and then of course exponential of epsilon 1 square plus epsilon 2 square plus v square by 2 sigma square. And there will be constants here, okay, which I am not going to keep track of. So this will be the distribution for the energy spacing within this. So we need to carry out this integral. So to carry out this integral, the typical trick that one does is to, well, there are many ways of doing it. I'm just going to do it, in the way I'm familiar with this. So I'm going to write this epsilon 2 minus epsilon 1, this quantity, as a new variable, root 2 times I. Okay? So define this. And okay, so and once you define this, then you can sort of see that this p omega now, so if I write just this part in terms of this variable, I can write epsilon 2 square as epsilon 1 square plus 2 root 2 xi epsilon 1 plus 2 xi square. Okay, that's the first step. Everyone with me here? I've defined this and just re-expressing epsilon 2 square here. Okay. Sorry? No, it's fine. Yeah. Sorry? Okay. And also this gap, square root of epsilon 2 minus epsilon 1 square plus 2v square, now just becomes root 2 times square root of xi square plus v square. Okay? Is that clear? So you see now why I did this. I mean, basically the idea is to take out at least one variable out of this delta function constant, so that that variable is just a Gaussian integral and I can do that. So what is that Gaussian integral? That Gaussian integral is that of epsilon 1 square. Okay, so because I have already sacrificed epsilon 2 here in favor of that. So the Gaussian integral that I need to do is d epsilon 1 exponential of minus epsilon 1 square plus 2 root 2 xi epsilon 1 by 2 sigma square d epsilon. Okay, with normalization constants and all that. Okay, and this integral one can do. Right? So what do? You basically complete the square, okay, and the integral then becomes a number, which will give me a number out here. But interestingly, this would give me a factor of xi square. I guess I'm okay, yeah. Something like that, okay. So if that is the, so see, the point is if that's the case, then I can simply carry this n outside, and therefore my p of omega now becomes some n prime d xi dv, and this one, because remember there was a minus 2 xi square out here, and then there is a plus xi square, so this would give me a minus xi square plus v square by 2 sigma square, and delta of omega minus square root of xi square plus v square times root 2. Okay. So I have now reduced at this integral to at least 2 variables instead of 3. Okay. Is that part clear? Everybody with me? Or any questions that I need to take? Okay, so let me now carry on with this. There is just one more step to doing this integral. And the reason I am doing this integral is, similar things will appear in many places of doing these multidimensional integrals in clever ways. And we are going to see how to do that when. So this P of omega, therefore, okay, so now what do I do? You see that this obviously has a suggestive form, that this is like the radius square of some variable, and so the thing to do is to define, for example, V as some R cos phi and xi as some R sin phi. Okay, and you see that this P of omega and this thing d xi dv, therefore would be, as you know, would be some R dr d phi. And you see that the d phi integral is trivial because there is no phi dependence in the integral anywhere. So we are only left with the R integral, which again up to some constant in double prime comes out to be dr r exponential minus r square by 2 sigma square and delta of omega minus root 2r. Okay.
That should be dv.
Yeah, sure. Sorry. Yeah, thanks. Okay. So this integral is really simple, you see. So one can do this. I mean, just substitute omega in this integral. And you see that this quantity is some a, and I'm going to write this in a suggestive form, times omega exponential minus omega square by 2 sigma square. Okay. Now this P of omega, and the reason I didn't keep track of these constants now is that I'm simply going to normalize this and get the coefficient. That I can always do. But the point about this is two things. Okay. So, okay, the first thing is that I could have repeated this whole exercise with yeah, that's right, omega square over sigma square. That's right, thank you. Okay. So the point is that the first statement, I could have done a similar thing with V and V star, that is when this thing are unitary. And my claim is that all I'm going to get is, instead of omega, I'm going to get an omega square here. Okay, this power will change, but the form is not going to change. In fact, I can generically write P of omega as some a beta omega to the power beta by b beta omega square, where this beta is 1 if you have a Gaussian orthogonal ensemble, that is your matrix elements are real, or 2 if you have a Gaussian unitary ensemble, that is these are complex numbers. Okay. This second analysis follows exactly same as the first, and I would urge everybody to repeat this. If you, sorry. Oh, b beta is some constant which comes in the coefficient of this. This will probably be 1 over sigma square, but I'm going to say in a minute why I have written this generically. But okay. But before getting into what these A's and B's are, this is one of the central results of our guess or intuition, of Wigner's intuition, that this matrix element of Hamiltonians are random numbers. Now, what does it tell us? One thing that it tells us is the phenomenon of level repulsion, which is a very interesting and which is a very important thing that comes in any many-body quantum system, that the probability that your energy gap is 0 is essentially 0, which essentially means that if you take two levels at random, they are never going to intersect, which essentially means that there is a repulsion between these two levels, and this phenomenon is typically called level repulsion, and it follows from this analysis. So this is one thing that was typically seen in complex spectra, and this is something that this random matrix theory gets right. Okay. The second thing is that the probability of having large energy gaps between levels essentially falls down exponentially in omega square. Okay, so it's a Gaussian decay. So out here, which essentially means that if you are, if you see a very complex system with lots of energy levels, there is a very good chance that these levels are going to be really close to one another. Okay. Because the energy gap being large is a very, is a very improbable event. So essentially what happens in this many-body system is that if you go right into the middle of the spectrum, the energy gap becomes exponentially small compared to the length of your system or dimension of your system. So they are really closely packed. However, you can have a small energy gap towards the end of the spectrum, which typically do not follow this kind of behavior. Okay? So these are the two things, closely spaced levels and no level crossing or level repulsion is something that this random matrix theory gets correct. So, yeah, any questions on this? So then I can proceed to the, yeah, so one by one, yeah, Shaptadip please. Yeah.
So even we started with the uncorrelated matrix elements, turns out that the eigenvalues are correlated.
Random but correlated.
So is it generically true, or is there a certain condition that one can get uncorrelated eigenstates?
No, we are going to see that. Just give me 1 second. I mean, we are going to see when energy levels itself can be uncorrelated. That's a very important part. I'm going to come.
Joint probability will be written in separate probability distribution of the fields.
Joint probability of what?
Joint probability of the eigenvalues.
Yeah.
Will be written as the individual probabilities.
If they are uncorrelated, that's what you're saying, no? We are going to see where that comes. Just give me 1 moment, okay? Yeah.
I was just asking that we start by sampling E1, E2 and V from Gaussian.
Yeah.
Why is that a necessary thing?
No, for two-level system, there is no reason why this has to be Gaussian. But imagine that you have now a multi-level Hamiltonian, and there are lots of these matrix elements. And if you have a lot of random numbers by central limit theorem, you are going to guess that they are Gaussian. I mean, that's the simplest thing to take into account. Okay.
So this result applies to that part of the spectrum where the density of states is a constant.
Yeah, so that we are going to come in the next lecture a little bit. Yeah, density of state has to be a constant. And the point is that if you take a small enough window, within that window, the density of state can always be constant. So if you just get your result by sampling states out of, this is probably not me, okay, or maybe me, but is there some, so should I put my phone out? Does that work? Hello? Yeah, okay, maybe. So, so apparently, if you take random states within that energy window, then and compute properties of several things, no. Hello? Can you hear me? Okay, let's try this. I've lowered this a little bit. So, okay, so if you do that, then the behavior that you are going to get is going to mimic this behavior. That's the statement. Yeah.
Can you explain what's the significance of this box equation?
Oh, it tells you how the energy gap behaves as a, what is the probability distribution of the energy gap in this system, in this complicated. So we of course said that, we don't know about individual these things. So we have said that these are random numbers. But then we can ask that, if I just take my level spacing, gaps one by one, and just sort of plot, what their value is as a function of energy, then the statement is that this is what they're going to follow. apparently two important things. One is that there would be no zero energy, so there would be no gapless modes. There will be this level repulsion. And the second thing is that extremely large gaps are also equally unlikely. They are going to fall up in a Gaussian manner. Okay? Is that? Yeah.
So will this conclusion also hold if we consider this epsilon 1, epsilon 2, V to be of like Poisson distribution or some other distribution?
No, it's going to change.
How will it,
Sorry?
how will it change? Like it will be.
Well, that you can calculate it. Yeah. I mean, I don't know how it will change, but that's not a typical distribution to take. Poisson will come in another setting. I'm going to come to that in a moment. Yeah.
This derivation is valid for two-level system.
This is valid for two-level system, yes.
So this kind of
Yeah.
It works for.
It does work for so at least this form, okay? So not everything works, but at least this form, this works for the multi-level system.
Why is this kind of valid?
Just give me 1 second. I'm going to come to that here. So yeah.
So here the eigenvalues are actually Gaussian distributions, but when
Eigenvalues? No.
that's the
Matrix elements.
matrix elements.
Epsilon 1, epsilon 2, and V. Matrix elements are Gaussian, independent Gaussian distributions.
So what about the orthogonals and unitary ensembles of this Gaussian elements?
No. Okay, so orthogonal because everything is real, and unitary when V and V star are different. So we have worked this out for the orthogonal case, and I would request you to work this out for the unitary case. Okay. Yeah.
Can you repeat your comments about this being valid in the mid-spectral region, not in the...
No. All I am saying is that, see, first of all, if you take a bunch of, a small energy window where this density of state is constant, for this kind of statistical analysis to take place, you need a lot of states out there. So naturally, in the mid-spectrum region where the density of levels is high, there you expect it to be valid. Okay, so that's a.
Yeah, so sorry, one more question. So if I take a non-integrable many-body quantum system, is it true that I can always find an energy window for which
Yes.
it is true?
Yeah, where the random matrix theory would hold, but that's a really small energy window. ETH, which I'm going to come to in the next class, does much better. It can take a small energy window, but that it can continue it over a range of energies. So we got an energy dependent answer. So I'm going to come to that. This is much more restrictive. Okay, so let me move on. So these two properties are what is interesting. Okay, and the point is that the other thing that you can ask, and I have no way of deriving this, so I'm going to just state the result. And this was Wigner's initial guess, and then maybe I can just pull this up and bring that down. Okay, so this was Wigner's original guess that if you have a system like this, then the density of state, rho of epsilon, is going to go as some constant times square root of d square minus epsilon square, where d is the level width, the width of the entire spectrum. Okay, and this, if d is large, so if I plot this, okay, very bad plot. So if d is really small, this would be like a peaked this thing, but if d is large, this is going to be constant for most of the. So the point is, in the middle of the spectrum, the constancy of the density of state from this kind of behavior is expected, and this density of state is this Wigner's semicircular density of state. The derivation of this is really complicated, and I'm going to skip this. But this was initially put in as guess by Wigner, and then later, there are some complicated mathematical ways of at least at least it has numerical support, and there are some complicated mathematical ways of deriving this, which I don't quite understand. So I'm going to skip.
If you have this rho epsilon, what happens?
Oh, if D is large, okay, so if you're, then the density of state takes a form like this. This is for large D, okay. And then,
Large dimension.
yeah, if you take a small cut out here, the density of state is more or less a constant. And there all this random matrix theory will hold. And it holds for majority of the.
So you are making this statement which is.
No, all I'm saying is that if this density of state holds, then there is a way of justifying why we are taking a constant density of state. That's all. For majority is part of the spectrum inside this.
This density of states is for random matrices.
This density of state is for a complicated quantum system within this, so if these are completely random. Okay, so let me move on and then talk about what happens to the eigenfunctions of this stuff, because I want to calculate some expectation value of operators and stuff like that using this random thing. So if I take, so now consider that I had this Hamiltonian whose elements are, this kind of Gaussian uncorrelated numbers. If I compute psi alpha, one of the eigenstates, okay, and I express it in a basis, an arbitrary generic basis, then this can be written as some Cn alpha n. Okay. Now that's straightforward. Now the question is that this Cn alpha, so the question is that what is the distribution of these Cn alphas given that H is random. Now the distribution of Cn alphas out here are guaranteed by two things. The first is that if you have a Gaussian orthogonal ensemble and if you make a orthogonal transformation to that, or for a unitary ensemble and unitary transformation on that, these eigenfunctions are going to remain the same. Okay, it doesn't matter because those ensembles doesn't care. Then the only thing that is left is that they need to, the probability of these Cn alphas is fixed by normalization. That's the only thing that they are going to care about. Okay? So this is equal to some delta function . So if they are real, then this is that, and if they are complex, then that's the thing. Okay. These are just numbers whose probability distribution is fixed by this normalization. Okay. And therefore, if you average this over this entire set, okay, this so these are like, for this real part, since we are doing the orthogonal part, these are like orthogonal unit vectors, okay? And if you average over them, say Cm beta average, okay, then the total number of them is D, because that's the number of eigenfunctions that you have. So there should be a 1 over D, and then there would be a delta alpha beta delta Mn. Unless n is equal to m and alpha is equal to beta, they are just going to be 0, because these are like random vectors. And well, if n is not equal to m, you can see why this is the case, because if you take psi alpha, psi beta, you can think about it, why this is not equal to 0 for n not equal to m. But the point is that because these are orthogonal random unit vectors, unless alpha is equal to beta and m is equal to n, this is going to go to 0, and the rest is just a normalization. Okay.
So like even if they are not, I can always do a transformation such that they something like that?
Sorry, what is that?
No, like even if they do not satisfy this equality, I can do a transformation.
No, they will always satisfy this equality.
In any generic basis.
In a generic basis, that's the thing. I mean, if you take a very special basis, they may not, but if you take a generic basis, they will. Okay. Okay.
Is there another kind of averaging going on when you say generic basis?
No, it's just that, this whole idea about this thing being a random number, uncorrelated random number, that holds in a generic basis. For example, think of, take a Hamiltonian and put it in your Fogg basis, the typical thing. That's not a generic basis, and that's why your Hamiltonian is sparse. Random numbers are typically not non-sparse, right? So you have to be in a generic basis to have this thing. So it's very important to realize that, Hamiltonian being sparse in a Fogg basis, and Wigner's surmise that they are random numbers in a generic basis, these two statements are not in contradiction with one another. That one should realize. Okay. Okay.
So, sir, we are writing that wave function, that psi as some coefficients times n, and these coefficients are random.
Orthogonal random unit vectors, and
that's how we're getting.
That's the property. Okay. So now the only thing that I want to do is to basically it has come to the end of this, so let me erase something. So now I want to calculate the expectation value of an operator, in this basis. So you see that if I calculate expectation of O, the matrix element alpha beta, which is given by psi alpha O psi beta, this is equal to summation over m and n C m alpha star C n beta, and then m n, okay. Okay. And now I want to compute this in an average sense. So I take a bunch of these states within this energy window and then average over this. So this quantity O alpha beta would be just this, okay. And therefore this would be summation over d, 1 over d, and because then now alpha has to be equal to beta, there would be a delta alpha beta coming out. And this quantity is just summation over n mod, so summation over n, n o n. Okay? It's just the diagonal matrix element, because you see the delta mn coming from here is going to force m is equal to n, and I can take one of the sums, and then this quantity is just this. So it tells you that this quantity is O average by, and because this 1 over d is just the total number of states, this thing tells you this quantity is just O average, okay. So this is just O average times delta alpha beta. Okay. So random matrix theory predicts that, if you have expectation of an operator which has weight within the states psi alpha and psi beta, then the average value of this is just going to be some O average, and it's only going to have diagonal elements. Off diagonal elements are 0. Okay. Similarly, if you do a slightly more complicated calculation, okay, let me try to erase this. Sorry? No, here there is no concept of, I haven't defined that. That will come when I do ETH, but yeah. But, it's somewhat in there because it has to have proper matrix elements within this. But for random matrix theory, it doesn't matter that much. For ETH, it will. So, okay. So now, the other thing that happens, and this is another thing that you could just work out, is that what happens when you take the correlator, so the connected correlator of such operator, So this is alpha O square alpha minus alpha O alpha whole square. And you can show that this thing goes as trace O square by D times some numerical factor which is 3 minus beta. Okay. So I'm not going to derive this result, but you see the fact that it goes as trace O square by D is something that you can immediately see from here. You know, because so what will happen is that, you know, when you do this, you have to take a expectation value of 4 of these coefficients for the average. And then because it's Gaussian, these are Gaussian uncorrelated random numbers, you can show that, you know, this 3 minus beta is going to come in. And it's only trace O squared that's going to come in. So we have found that, you know, the expectation of this O square is given by trace O square by D times a factor which is 2 if you have Gaussian orthogonal ensemble and 1 if you have Gaussian unitary ensemble. Okay. Therefore, if I now want to make a generic statement about the matrix element of these operators in an average sense, then I can write my O as some O bar delta alpha beta, O alpha beta that is, plus this quantity trace O square by D times some random number R alpha beta, which has variance 1 and mean 0. So that when you take the expectation value of O alpha, trace of O alpha beta, you are just going to get an O average, and this is going to give you the property of the variance. Okay, of course, there will be a factor of 3 minus beta, which I am not keeping here, but this is generically the prediction of random matrix theory for matrix element of operators. Okay. See, the point is that this is something which is a bit different, so let me spend a minute or two on this. See, the thing is that when we talk about a quantum mechanical system, so we of course diagonalize the system and then we have eigenvalues and eigenfunctions and everything. However, we don't really think about having structures in expectation value of operators, local operators for example, okay? Random matrix theory, on the other hand, essentially tells you that, well, you know, if things are pretty complicated and if all these matrix elements are Gaussian random numbers, they are going to have some ramification not only in the properties of eigenvalues, but also about properties of eigenfunctions, and therefore properties of all the expectation values of local operators or operators in general. So essentially, they assign a structure to the matrix element of these operators and in the energy eigenbasis. Remember, alpha and beta were the eigenfunctions. Okay? Psi alpha, psi beta were eigenfunctions. So in the energy eigenbasis, this thing is going to come back and haunt us when we essentially do eigenstate thermalization hypothesis. You know, essentially eigenstate thermalization hypothesis is one more level of sophistication of this particular thing, assigning a similar structure to local operators. But that's for tomorrow. But the point is that this is the result along with P omega, which is some A beta omega to the power beta exponential B beta omega square. These are the two main statements of random matrix theory. One is about level repulsion and exponential Gaussian fall-off of energy gaps, and the other one is assigning a structure to expectation value of operators. Okay? Yeah?
So I understand the first one, O bar, delta, alpha, beta, but why do you add the second?
This is just to ensure that this holds. This is another way of saying that this variance is the same. And because it's Gaussian, once you know the variance and the mean, that's it.
R alpha beta, any
Oh, that's a R alpha beta are generic random numbers with unit variance and zero mean, Gaussian random numbers. So in some sense, you are taking the randomness and putting them in this stuff and adjusting the amplitude.
So this structure for O is, when is it valid? Are there some conditions on?
Yeah, we are going to discuss those conditions in the next lecture. Okay. So for now, let's just, yeah.
There are two things here. One is this bar that you write, which you call average, and other thing is expectation value in the quantum.
Yes.
So what are these two things?
So expectation is like the quantum expectation, you just take the expectation of an operator given this. And this is averaging over a set of states within that energy gap. Bar is like,
So it's not like you take 10 random matrices and then you take an average.
no. Okay. So, and also, just for the sake of it, if I look into this thing, this P of omega as a function of omega, I should just draw this. And it will come out to be something like this. There is a peak in the middle and, 0 for omega equal to 0, 0 for omega tending to infinity, and there is a peak in the middle. And we are going to calculate what this mean level spacing is. Yeah?
Sir, I could see how the energy gap is suppressed and the graph also illustrates that. But I'm not able to understand how does that equation implies level repulsion.
There is no gap 0. So two levels never cross, and therefore they repel. Okay.
So this averaging has to be somehow linked to the different realizations of the random matrix.
Yes, yeah. But in a many body system, since there are so many of these anyway, if you average over, yeah, they are self-averaging procedure. Okay. Within that energy gap. See, this is the thing, that this energy gap has to be small enough so that the density of state is a constant, but it has to be large enough so that there are enough number of states in there. And this is where many body things, this many body systems save you in the sense that the energy gaps are exponentially close to each other. And that's why you can do this actually. Okay, okay, if not, let's just move to another class of systems where this thing doesn't hold. Since we have seen some things, where there are some very nice formula, let's just see why this doesn't hold. And these are typically what is called integrable systems. Okay. Now in integrable systems, what happens is that apart from energy being a conserved quantity, as in any Hamiltonian system, there are a large number of, almost a thermodynamically large number of conserved quantities. So for example, if you take Ising model in a transverse field, which is an integrable system, you convert it into fermions, and then the occupation number of each of these modes of these fermions is conserved. Okay. You think of free fermions, again, density at each k mode is conserved, and so on and so forth. Okay. So these essentially completely changes the structure of this theory. Why? Because let's say that I have solved this model and I have got some energies as a function, individual energies as function of epsilon k. Just think of some harmonic oscillators or free fermions or things like that. The simplest way to understand that. So if I now construct a many body energy E, then clearly this would be like nk epsilon k, where nk is the occupation probability of a given level, occupation number, and k is that. And these nks are all conserved. Okay, they are known numbers. Therefore, you see that, now think of this E being very large. So you are considering high energy state in the middle of the spectrum. Now, clearly, two energies E and E plus dE may have very different nks, distribution of nks, because if these are ones and zeros, I can construct them in many ways. And if I change this energy just a little bit, this distribution is completely going to change. Okay? And therefore, these E's in a complicated enough systems are uncorrelated random numbers. Okay? So notice the difference. In the previous case, I had matrix element in an arbitrary basis as Gaussian random numbers. Here, these E's are completely uncorrelated random numbers. Sorry? Oh, because if I change this E to E plus DE, you know, these distribution, this n case completely change, can completely change.
You were claiming that they are uncorrelated.
They are uncorrelated because, you know, I'm not doing anything to the epsilon case.
Is it just based on intuition or?
No, you can check because you see the point is that if you think about it, so I construct an energy E, right? So let's say that I take various values of these n's and stuff like that, okay? The wave function of course are going to depend on these values of n. Now I construct an energy E plus D. These values of n can be completely different. It's just like, you know, you are trying to build a large number out of adding different small numbers. And usually
that is also dependent on the epsilon. If I am just changing E to delta E, so how
no,
do I
if
use the NK, that also depend on epsilon.
epsilon meaning this? Yeah, but these are single particle energy levels, and E, as I said, is a very large energy. So there are lots of these epsilon k's out there.
I mean, this has to be true by proper logic, then this has to be true in low energy also.
No. E has to be large, otherwise this property is not going to come.
This is kind of limiting.
I'm saying that, you know, if you take E to be large compared to, let's say, epsilon k, you know this, and then you need to add lot of this. It's a bunch of numbers that you add. You change E to E plus del E, the distribution of these numbers may completely change to give you E plus del E. That's all I'm saying. Okay. This thing goes by the name of Bery-Tabor conjecture. Okay. The fact that these are these would be uncorrelated random numbers. Okay.
What are uncorrelated? This E.
E's. The energy eigenvalues themselves. E's. The many body energy eigenvalues themselves. Okay, and the difference is that in the previous case it was the matrix element of Hamiltonians in a given basis which were independent random numbers. Here the energies themselves are, and that is the case because of the presence of these conserved quantities. Because you can write it like that. Okay.
So these NKs can be adjusted independently of one another.
Yes.
Such that the sum is.
Sum is, yeah. So, and there are many ways of adjusting that. Okay. So that's the whole point. Okay. Now, if this happens, then clearly, you know, there is no way that, so there is no, so you can see that if these levels are completely uncorrelated, they can have different values and they can cross each other happily because, you know, they are completely uncorrelated. There is no telling as to how they would behave as a function of parameter.
Just resolve this symmetry. I mean, in this example, probably it's difficult, but let's say in another situation where let's say this kind of symmetry can be subsymmetry.
It's not a symmetry. It's just these conserved quantities that we have in an integral, and there are large number of them.
So if I go to the projected sector.
What do you mean?
So let's say you have a conserved charge.
No, I have already gone to all these and solved, and those are your epsilon k's. But now if you want to calculate the many body energy levels corresponding to large number of occupations and stuff like that, then this is the way you do it, right? What other ways are there?
We are already given a given set.
You mean symmetry in the sense of global symmetry?
Yes.
No, forget about those. We are already within a given symmetry sector if there is. I mean, I'm not even, so think of a system which doesn't have any. That's the simplest step. I'm sorry, I didn't understand. Yeah.
It's because epsilon k is fixed. You know epsilon k.
I know epsilon k and I also know my nks,
NK.
but there are lots of them.
Lots of them.
So for large energies, I need a sum of lots of them. That's why we can do this.
Yeah, that's why you need large E, because then you have more possibility.
But if you didn't know epsilon, then
No, then of course, no. But in integrable models, you typically do.
yeah.
So the probability of now having, so now I again take this delta E, okay, a small energy gap, and I ask myself what is the probability of having, let's say, n such levels, energy levels E within that energy gap. Okay. Given that there are, this large number of these NKs, what's the distribution? Yeah, so suppose I ask you what is the probability of having n such random, n such levels within an energy spacing delta E, some d, some, so what's this distribution? So the answer to this is that since these are completely uncorrelated, the answer is Poissonian, okay? And because it's Poissonian, and if I declare this average number of levels within an energy gap as some lambda, then I can write this as lambda to the power n, p of n as lambda to the power n by n factorial minus exponential lambda. Okay. Therefore, the probability of having just one state within an energy gap, or rather zero state within an energy gap P0, is simply exponential minus lambda. Okay, but having zero state essentially means your energy gap, right? And therefore, the statistics of this energy gap is also Poissonian, exponential.
What's lambda?
Lambda is the average energy gap. It's a parameter. So basically, if you have capital N states within an energy E, then lambda is E by U. That's the average energy gap that you are going to have. So this is exponential minus lambda, okay? So here you see that this distribution, remember previously we had to go through many different things, and we got a P of omega which looked like this, and it showed level repulsion. Here, because of this concept quantity, the P of omega versus omega just falls like this. Okay, very bad drawing, sorry about this. But the point is that here there is a large number of states which cross each other, which can cross each other, and P of 0 goes to 1 there. Of course, this one is to normalize everything properly and stuff like that, but the point is that, there is a normalization factor, of course, everywhere. That needs to be properly normalized.
So lambda is the mean of this.
Mean, yeah.
So mean, like
mean level spacing.
Average number of.
Mean level spacing.
Is the average number of levels within.
Yeah, but if you consider zero energy levels within a given energy spacing, then it's just a gap.
Okay.
Yeah.
So how did you calculate that the probability distribution of energy gaps will be Poissonian?
We didn't really conclude that, but the point is that if they are completely random, uncorrelated, and there are lots of them, then typically these kind of these things follow a Poissonian distribution, right? If you have a lot of uncorrelated random events.
But usually people think of CLT in that case.
Think of what?
The central limit theorem, so people would guess.
No, that's different. You see, these are completely uncorrelated random this thing. So they are going to follow a Poissonian distribution.
I think you can get that. If I take n such variables and perform the integrals, this e to the minus exponential will come
out, yeah, but so, okay, we can do the math, but if you think about it, that's a basic probability, this thing.
Here the joint probability is decoupled.
Yeah, here the joint probability is decoupled. Because they are uncorrelated, their joint probability has to be decoupled, and that's one way of seeing why it is going to be. Okay, in the last, I have 20 minutes, good. So now one thing, so we see that there are these two different distributions. One for this integrable model which comes from Berry's conjecture, and the other is when you don't have integrability, that is for chaotic systems where they have level repulsion. So now the question is, suppose somebody gave you a many-body system with some Hamiltonian, how do you know? Okay. So of course, here because we took very simple systems, we essentially can say one is either Poissonian or the other one is not and stuff like that. But given a real life Hamiltonian like this, there is very little way of knowing a priori whether the system is integrable or not. Particularly, a Hamiltonian may seem non-integrable but may turn out to be integrable or the other way around. I mean, it's really complicated. So to do that, one needs to have some diagnostics as to what do you do. Now, the simplest diagnostic that people usually use is something called a level spacing ratio. Okay? And we are going to see how these level spacing ratios look like in case of both this ergodic systems and the Poissonian system. That's the last few minutes of this lecture. Okay, so can I? Maybe I can use this. Yes, the other part. Okay, so basically, so what we are going to define is this adjacent level spacing ratio. That is, you take an energy level n and another energy gap. So take these three levels, n, something like that. Out of this, you can define two energy gaps. Two adjacent energy gaps. One of them I'm going to call as delta n minus 1 and the other one I'm going to call as delta n. Okay. Fine? Now, since there are these two gaps, first let me use this for the integrable model and see how it comes out. So since there are two gaps, this probability of S1, S2, that is these two gaps, if I call them as S1 and S2, any two gaps, S1 and S2, is simply going to be exponential of minus S1 plus S2 times some normalization, which I need to fix, okay? Because they are uncorrelated and the joint distribution is just the product. Now the point is that what I need to calculate is the adjacent level spacing ratio, which is given by minimum of delta n minus 1 by maximum of delta n comma delta n minus 1. Okay. This ratio goes from 0 to 1. Okay. And so I'm going to define this as S1 over S2 just for choice. Okay. I could, if I did this as S2 over S1, the result is not going to change because you see that the probability distribution here doesn't change if you have.
Just tell me what is S1?
So the gaps are delta n and delta n minus 1. Okay. So the minimum of those is either delta n or delta n minus 1. Whatever that is, I call it S1. The other one I call S2. Okay. Fine? Questions? Okay. So now, Therefore, here this P S1 S2, and this calculation is really simple because these are uncorrelated. I can write this as P R and S1, R being this ratio of this level spacing, and because this is defined as S1 and S1 by S2, I can write this as exponential minus S 1 plus R n. Sorry, S1 1 plus R n. Did I should have. Okay, so I'm going to define this as S2, okay? Sorry. Okay? Fine. So now what do I need to calculate? I need to calculate the probability of having R to be some fixed value, right? Are you guys with me or? So I need to find out what's the probability of having R to some fixed value, which means that in this distribution, if I integrate out S2, then I'm going to find the probability of R, probability distribution of R. So P of R is integral ds2 exponential of minus S2 1 plus R, and then one is to find out the Jacobian of this transformation. Because you see that I initially had my variables S1, S2, but now I am going to R, which is S1 over S2, and then keeping this S2, okay, equal to S. So I need to have the Jacobian between these two, okay. And this Jacobian is just this inverse of the determinant of the derivatives. And if you calculate these derivatives, del R del S1 is 1 over S2, del R del S2 is minus S1 over S2 square, and del S del S2 is 1, del S del S1 is 0, okay. So put this back, take the inverse, take the determinant, and you are going to see that this quantity is going to just come out to be S, okay. And when you do this, you will find 2 by 1 plus R whole square. The fact that it will be 1 plus R whole square can be just found by scaling, because if you scale this integral, this variable S by 1 plus R, you see that there would be a factor of 1 plus R whole square, and this 2 comes from normalization, okay. That's the idea. Sorry? Yeah, S can go from 0 to infinity, I guess, right? Yeah, so I should write this. Okay. Now, let me, with this P of R, I can now compute the average level spacing. Now that's straightforward. So let me guess this part. This P of R, therefore, is 2 times R by 1 plus R whole square dr, and this should go from 1 to 0. Okay. Okay. What is this integral? Now this everybody should be able to do. Oh, sorry. This is average R. Okay. R, which is equal to integral R P of R dr. 1 to 0. Sorry. Thanks for pointing this out. Okay. This integral, if you do this, is going to turn out to be, and this is something you should really work out, 2 log 2 minus 1, if I am not mistaken. Yeah. And this quantity is 0.385, if you essentially look into this. And this is this, reasonably well-known result that for a integrable model, the average level spacing ratio falls to 0.39. Okay. Okay. Is that?
Why the limit is from 0 to 1?
Oh, because it's the ratio of minimum and maximum. So it can only go from 0 to 1. Yeah.
Can you tell why you started with that joint probability being in that expression?
Which one? This? Because these are uncorrelated. Their joint distribution is just the product of the two probability distributions.
So you're having this Poisson distribution.
Yes. Yeah. It's just PS1 times PS2. Okay, anything else? Yeah.
So the model is integrable if it is less than this or greater than this?
No. If the model is integrable, and if you, so when you do your numerics, with all this, so what do? You diagonalize your Hamiltonian, you find out what your energy level is. Then numerically you compute this R, okay? If that value for a large enough system size approaches close to 0.4 or this 0.39, 386 is the exact number, then you have a good chance of having an integrable system. So in the next class probably, because I'm just, I think I should end here because it's just 10 minutes and it's probably better to take that up in the next class. See, the thing is that when we do this for the Gaussian, the ergodic systems, okay, where this probability distribution was different, and we're going to talk about that in the next class, we'll see that this number goes to somewhere close to 0.5, okay. Therefore, there is a difference that you can pick up in your numerics, whether that average goes to close to 0.5 or close to 0.4, and I'm loosely talking about numbers, there are exact values of that. So I think it's 0.53 for GUE and stuff like that, but you can really make that difference, okay, and you can see if the model is integrable or not. And that's one of the standard diagnostics for finding out integrability in a many-body system. So in the next class, what I'm going to do is to sort of give you a sketch. I'm not going to do the full calculation, but give you a sketch of how to do an analogous thing for these ergodic systems. Okay, what's the statistics of this average R? And then what we are going to do is to have this thing in the background, this random matrix theory, and then talk about how eigenstate thermalization hypothesis in some sense provides one layer of improvement over this random matrix theory, and how it sort of bridges between the results of quantum mechanics and statistical mechanics. Okay, so that would be the next class. So I think I have bored you enough, so let me stop here at the moment, and thank you for your attention.
So if is there any more questions? Oh.
So you mentioned this 0.3 and 0.5 region. So can level statistics go out of this region?
Yes, so in principle it can be in between this, and that can happen because of finite system size effect, because these are all for thermodynamic systems, so if you have a finite system size, there could be system size induced sort of fluctuations which can change the statistics. There are also other ways in which this can happen. Mostly when you are doing driven systems, there is a version of this where things can happen because of some other reasons. But yes, but those, for most of the times, particularly when one does numerics with finite size systems, one understands those differences, why this is. And I have never seen anything go, at least in this many-body systems that at least we have looked into, which are described by the short-range Hamiltonians, kosher kind of things. So we have never seen anything which goes above these numbers. In the range between 0.4 and 0.5, many times it is possible, actually. Actually, can we, okay, so before I end, I just wanted to show you one plot. Can I just, yeah. Sorry, I almost completely forgot about this.
So we have time, right?
Yeah, it will just take 2 minutes. So, yeah. Is there a pointer by any chance?
Before you show this, I have one question.
Yeah.
Here.
Yeah, sure.
Yeah, so here we always talk about the level spacings, but don't we talk about the eigenvalues, like if the eigenvalues are uncorrelated or not? I think you mentioned that you will talk about when the eigenvalues are uncorrelated.
No, because the point is that, you see, you can have the distribution of eigenvalues and check this, but then one has to take into account this density of states. And this has to come, this level spacing ratio is independent of the density of states. That's why it's typically taken as the standard measure for this kind of things.
Okay. And is there any like particular proof that the thing you were telling, that if the density of states is constant within the range, then the whole analysis works through?
Yeah. That's where the prediction is going to sort of work.
Okay.
Otherwise, you are going to see deviation from this.
Can you give any reference to that?
Yeah, I'm going to give the reference. I mean, tomorrow when I finish, you know, I'm going to sort of give all the references.
Thank you.
Okay. So just wanted to show this plot, this one thing. So, okay, so this is taken from a review that Anatoly Polkovnikov, Marcus Rugal, Kafri and this other guys wrote, and this is an excellent demonstration. Do I have a? Okay, I think. So I took. Is there a pointer by any chance somewhere? This one. Okay. Good. Okay. So basically, you see, this is the Hamiltonian. Okay. Now, this is a free fermion model, provided you set this v, v prime, etc., all to 0, and j prime also. There, you see how simple the Poissonian statistics look like. Okay. This is exact numerics. And when you have j prime and v prime to be large, you see so these black dots essentially are the real numerics, and the blue and the red lines are the fits, one from the Poisson statistics and the other from the Wigner-Dyson, okay, for Gaussian orthogonal ensembles. And here you see that these, when you have reasonably large values, this essentially almost goes to the Wigner-Dyson. Here it follows Poisson. Okay. And in between there is a crossover. So if the thing is small, there is a crossover regime in between where this moves from one to the other, and there, as you asked, things can be different from either prediction. Okay. So yeah, so this I wanted to show just for the sake of having a demonstration that this actually works in a standard many-body system. So yeah, that's it. Thanks.
So for chaotic systems, it is the
red curve.
The red curve, and for integrable systems, the blue. And the in-between systems, are they also chaotic or?
No, they are chaotic. You see? Never mind. So something happened. Yeah. Sorry. So you see out here, for example, okay, where j prime and v prime is small, and you basically are somewhere in between. You still find that there is a level repulsion. Okay, that structure is there, except that this really hasn't gone into the red curve yet. Now, why does this happen? Now, this is one of the examples of the finite size effect that I was talking about. They are doing numerics with a finite chain with L equal to 24. If this was not 24 and 240, you are not going to see this behavior. It would straight follow on the curve. Okay. So these are finite. This crossover is typically a finite size effect in most of the systems, and if your system size is large enough, you are not going to see this. Okay.
Any more questions? If not, let's thank the speaker.
Thank you.